Ever walked into a party and thought, man, I wish I knew some really cool science facts?
Oh, yeah, I've totally been there.
Well, today's your lucky day
Oh,
because we're about to arm you with some seriously awesome chemistry knowledge. Perfect for impressing even the most hardcore science nerds.
love it.
You sent us some really cool stuff about what you called black holes in chemistry.
Yeah,
5 factoids that highlight the most mind-blowing, irresistible forces in chemistry.
right.
Electron thieves, super strong acids, reactions that seem impossible.
It's all here.
I'm excited to dig into it.
Too. By the end of this deep dive, you'll be dropping knowledge bombs left and right.
Let's do it.
Okay, let's jump right in. Your first factoid features a real superstar in chemistry.
Okay.
Fluorine.
Fluorine.
High school chemistry is coming back to me in a rush.
Yes.
It's halogen, right?
Yeah.
Super reactive.
Yes, fluorine is the most reactive element on the entire periodic table.
Wow.
And it's all because of its incredible, insatiable hunger for electrons.
So it's like the ultimate electron thief. Exactly. Scientists actually use a term called electronegativity to describe this tendency.
Okay.
Think of it as how badly an atom wants to pull electrons away from other atoms.
So the higher the electronegativity, the stronger the pull.
You got it. And fluorine sits right at the top of that electronegativity scale. It's so electronegative it can rip electrons away from noble gases.
Wait, noble gases can react? I thought they were like chemically untouchable.
Right. That's what makes fluorine so interesting.
Hmm.
It can force these reactions we thought were impossible. And this crazy reactivity has some real-world uses.
Oh, I'm all about the practical stuff.
Well, think about Teflon, the non-stick coating on your frying pan. Its amazing slipperiness is all thanks to the strength of the carbon-fluorine bond. Fluorine holds onto those electrons so tightly that nothing can stick to it.
So every time I make scrambled eggs, I'm witnessing fluorine's electron hogging powers. That's kind of wild.
It is.
Speaking of wild, one of the other factoids you sent mentioned superacids.
Yeah,
Is this like sulfuric acid on steroids or something?
that's a good way to put it. Sulfuric acid is already super strong, but superacids take it to a whole new level. They're so strong they make sulfuric acid look weak.
Okay, I'm intrigued. How do you even measure something like that?
Scientists use a special scale called the Hammett acidity function.
Okay.
It's basically a measure of how much an acid wants to donate a proton. The lower the number, the stronger the acid-bacid. Superacids have values way lower than pure sulfuric acid.
So they're like the proton-donating champions of the chemistry world.
Precisely.
Yeah.
And this extreme power makes superacids really useful.
How so?
Well, they can start reactions that just wouldn't happen with normal acids.
So what kind of impact does that have?
Well, for one, they're really important for developing new materials.
Okay.
They can be used to make polymers with totally unique properties, or create catalysts to speed up reactions.
So they're like master chefs whipping up new molecular creations.
I like that analogy.
It's cool.
Yeah, and their ability to protonate pretty much any organic molecule opens up tons of possibilities.
This is making me rethink everything I thought I knew about acids. You know, another factoid you sent was about gold reacting.
Yeah,
I always thought gold was basically indestructible.
it's what we all think, right? Gold is famous for its stability, and it doesn't corrode. But even gold has its limits.
Wait, are you saying we can actually make gold react? How?
It comes down to finding an opponent strong enough to challenge it in a chemical tug-of-war. Something that really wants to steal electrons even from something as reluctant as gold.
So we need like a super electron thief.
Yeah,
Even stronger than fluorine.
exactly. And scientists have actually found these super powerful oxidizing agents, substances that can pull electrons away from other substances, even something as stable as gold.
Wow. And by exposing gold to this, we can actually make it react.
Yep. And the really cool thing is this ability to make even the unreactive elements react opens up so many possibilities for creating brand new materials with properties we haven't even thought of yet.
So even gold, the ultimate symbol of stability, can be transformed.
Right.
That's a powerful concept.
Yeah.
Makes you wonder what other impossible reactions are just waiting to be discovered.
It really does, and that's just the start. Your next factoid takes us even deeper into the periodic table, into the world of heavy elements.
All right, bring on the heavyweights. I'm ready for more.
Let's talk about actinides.
Okay.
Those are the radioactive elements at the bottom of the periodic table, like uranium and plutonium.
Oh, right. the elements that make nuclear things happen.
Exactly, and their behavior is anything but ordinary.
Really?
They have so many electrons whizzing around their nuclei that they don't always follow the normal rules of chemical bonding.
So they're like the rule breakers of the periodic table.
In a way, yeah. They form bonds in ways we don't totally get yet, and that makes them incredibly important for nuclear chemistry, but also super hard to study.
It makes you wonder what other secrets are hidden in those heavy elements and how they might change our whole understanding of chemistry.
Absolutely, there's still so much we don't know about them, and that's what makes them so fascinating to research.
This deep dive has already been a wild ride. We've gone from fluorine, the electron thief, to superacids, to proton-donating champs, and now to heavy elements bending all the rules.
And we're just getting started. Your next factoid takes us into the world of physics.
Physics. Wait, are we talking about Einstein and his theory of relativity now?
You guessed it. It might sound surprising, but even Einstein's theory has something to say about how atoms behave.
Okay, I'm all ears. How does relativity fit into all of this?
Well, in heavy atoms like gold, the electrons in the inner shells move incredibly fast. We're talking a significant chunk of the speed of light. And when things move that fast, relativistic effects start to matter.
Relativistic effects, like time slowing down and things getting heavier.
Exactly. And even though those effects might seem small at the atomic level, they can actually have a big impact on how electrons act.
So how does this explain the color of gold?
Well, in gold, those relativistic effects change how it interacts with light. And that's what gives it its yellow color.
Wait, are you saying that if electrons didn't move so fast, gold would be a different color?
Exactly. If we could somehow turn off those relativistic effects, gold might actually look silver like other metals.
This is blowing my mind. Who knew that the color of gold was basically thanks to Einstein?
It's a perfect example of how different areas of science like physics and chemistry are actually deeply connected.
This deep dive is already so fascinating. I can't wait to see what other amazing chemical forces we uncover in part 2.
Stay tuned! We'll be back soon to continue our exploration. Welcome back to our deep dive into black holes in chemistry.
Still processing all the mind-blowing facts from part 1.
Yeah, there was a lot.
Who knew gold could be silver if it wasn't for Einstein?
Right. Makes you think about all the hidden connections in science.
It really does. I'm ready for more surprises. What's next?
Well, so far we've talked about the most electronegative element, super strong acids, and those crazy reactive heavy elements.
Yep.
But this time, let's talk about something a bit more low-key. Noble gases.
Okay, noble gases. We talked about those briefly in part 1. When we were discussing fluorine's electron-stealing skills. You mentioned that fluorine is so reactive, it can even force noble gases to make compounds.
Exactly. For a long time, noble gases were considered completely inert, just hanging out, not participating in any chemical bonding.
Yeah.
But as we've seen, chemistry is full of exceptions.
So even the most standoffish elements can react under the right conditions.
Exactly. And the discovery of noble gas compounds totally changed the game in chemistry. It made scientists rethink how they understood chemical bonding and opened up whole new areas of research.
I'm sensing a theme here. It seems like chemistry is all about pushing the boundaries of what's possible.
You got it. And that leads us perfectly to our next factoid, which is all about taking oxidation to the extreme.
Okay, extreme oxidation. What does that even mean?
Well, we know oxidation is about an atom losing electrons.
Right.
And oxidizing agents are those substances that love to grab electrons from other substances.
So an extreme oxidizing agent would be like an ultra-powerful electron thief, even stronger than fluorine.
You could say that we're talking about oxidizing agents so strong they can force even the most stubborn elements to give up their electrons.
Including noble gases.
Yes. The first xenon compound was actually made back in 1962.
Wow.
Using a crazy strong oxidizing agent. It was a huge discovery that challenged what everyone thought about noble gases being inert.
So even the most stable, untouchable elements have their weaknesses.
That's one way to think about it. It shows us that stability in chemistry is all relative. It depends on the conditions and what other players are involved.
This is making me question everything I learned about the periodic table. It reminds me we haven't talked much about the other heavy elements.
You're right. We discussed actinides earlier, but there's another group we need to talk about. The lanthanides.
Lanthanides. I remember the name, but can't remember much else about them. Refresh my memory.
Well, the lanthanides are a group of 15 metallic elements. They have a special place in the periodic table, often shown in a separate row below the main body.
Oh yeah, that little island of elements.
Yeah.
Always seems kind of mysterious.
Exactly. And they are pretty fascinating. One thing that makes them special is their electronic structure.
Their electronic structure, how is it different?
They have electrons in a special type of orbital called the orbital.
Okay.
And these orbitals are kind of buried deep within the atom, shielded by other electrons.
So like the introvert electrons hiding from the party.
Uh-huh. That's one way to think about it. And this shielding has a huge impact on how they behave. It gives them some unique magnetic and optical properties.
Interesting. So what are lanthanides used for?
Oh, they're everywhere. You'll find them in high-powered magnets, lasers, even the color screens on your phone and TV.
Really? Had no idea those little guys were so versatile.
They really are.
Yeah.
And they're a perfect example of how understanding the tiniest details of electron behavior can lead to amazing technologies that shape our world.
This deep dive is full of examples like that, how chemistry influences everything from everyday objects to cutting-edge tech.
Absolutely. And there's more to come. Your next factoid takes us back to extreme conditions. But this time, it's not about oxidizing agents. It's about heat. Extreme heat.
All right, I'm ready to feel the burn. What happens when you crank up the temperature?
We're going to talk about plasma.
Plasma, like those cool plasma balls you could buy at science museums.
Exactly. But plasma is way more than just a toy. It's often called the fourth state of matter.
Wait, I thought there were only three: solid, liquid, and gas.
That's what we usually learn. But there's a fourth one, plasma. And it forms when you heat up a gas so much that its atoms start losing their electrons.
Just like a superheated, super excited gas.
Exactly. And this ionization gives plasma some unique powers.
Powers.
It can conduct electricity, emit light, and it responds to magnetic fields.
So a gas with superpowers.
I like that. And these superpowers make plasma really useful.
Like how? What's it used for?
You mentioned plasma balls, but it's also used in things like fluorescent lights, neon signs, plasma TVs, even fusion reactors.
Fusion reactors, the ones that could give us clean, limitless energy.
The very same fusion reactions happen at crazy high temperatures. So hot, they need plasma to keep going.
So plasma isn't just cool looking. It could be the key to solving our energy problems.
It has that potential.
Right.
Of course, there are still lots of challenges in fusion research, but it's an exciting field that could change how we power the world.
This deep dive just keeps getting more fascinating, learning so much about the power of chemistry.
And there's more to come. Your next factoid takes us in the opposite direction to ultra-low temperatures.
Okay.
We're going to explore what happens when things get so cold that even atoms start acting weird.
All right, I'm ready for the deep freeze. What's waiting for us at the bottom of the temperature scale?
We're going to talk about something called Bose-Einstein condensates, or BECs for short.
The ECs. Sounds like science fiction.
It might sound strange, but BECs are real. They form when you cool down a gas of bosons, which are a specific type of particle, to temperatures just a tiny fraction above absolute zero.
Absolute zero. The coldest possible temperature, right?
You got it. And when you get that close to absolute zero, something amazing happens to the bosons in the gas. They start to lose their individual identities and act as one big unit.
So it's like a bunch of individual atoms merging into one superatom.
It's a bit of a simplification, but you're getting the idea. In a BEC, all the bosons are in the same quantum state, meaning they all have the same energy and momentum. They basically become a single wave.
Wow, that's mind-blowing. Why are these BECs so important?
They're like a window into the quantum world. They let us study quantum mechanics on a large scale, which is really hard to do.
So they're like a bridge between the crazy world of quantum mechanics and the world we experience every day.
Exactly. And this has led to a ton of new research in fields like atomic physics, condensed matter physics, and even quantum computing.
It's like we're on a tour of the whole chemical universe, exploring all the extremes of temperature, pressure, and reactivity.
And we have one more stop on our journey. Your final factoid takes us to the world of material science, where we'll explore something called metallic glass.
Metallic glass. Isn't glass, well, just glass. What makes it metallic?
It's a bit of a funny name, but metallic glass refers to a special kind of alloy. It has an amorphous structure, meaning its atoms are arranged randomly, not in a neat pattern.
So it's like a metal that wants to be a glass.
That's one way to think about it.
Yeah.
And this structure gives metallic glass some cool properties. It's super strong, but also flexible and elastic.
That's a pretty impressive combo. So what are metallic glasses used for?
They're used in a ton of stuff, from high-performance sports equipment and medical implants to electronic devices and even aerospace components.
Wow, that's amazing.
Yeah.
So they're like the super athletes of materials.
Yeah.
Combining strength and flexibility.
Haha, I like that. And they really show how powerful material science is. It lets us create materials with specific properties that can revolutionize industries.
This deep dive has been incredible. I feel like I have a whole new understanding of the power and variety of chemical forces.
And we've only just scratched the surface. There's so much more to explore in chemistry, from how molecules bond to the origins of life itself.
I'm ready for more. But for now, my brain needs a break to process all this amazing stuff.
I hear you. We'll be back in part 3 to wrap up our exploration of black holes in chemistry. Until then, keep thinking about these incredible chemical forces and how they shape our world.
Welcome back. It feels like we've traveled to the hottest and coldest corners of the chemical universe.
It has been quite a journey through the extremes of chemistry.
For sure. And you saved one last factoid for us, something about black holes in chemistry. What's the final chemical marvel we're diving into?
This one brings us back to those electron thieves, but with a twist. Ever heard of electrides?
Electrades. That's a no one. Sounds like a superhero name. What are they?
They're a special kind of compound where electrons act as anions.
Wait, electrons as anions? I thought anions were negatively charged atoms. Like chloride or fluoride?
You're right, that's usually how it works.
Yeah.
But in electrides, the electrons themselves are trapped in little pockets within the material. They're not attached to any specific atom. It's like they're free electrons acting like ions on their own.
So the electrons have gone rogue, formed their own little society.
Uh-huh. That's a great way to put it. And these rogue electrons give electrodes some pretty cool properties. Like they can be super powerful reducing agents.
Reducing agents, meaning they're good at giving away electrons. The opposite of those oxidizing agents we talked about.
Exactly. Electrodes are like the ultimate electron donors. And that makes them potentially useful for all sorts of things like catalysis or electronics.
So we could use them to make reactions happen or even build new electronic devices.
That's the hope. Electrodes are still a pretty new area of research, so we're still figuring them out, but they have huge potential.
It's amazing how something as small as an electron can lead to such big innovations.
It really is, and it shows how chemistry is always surprising us. We think we've figured everything out, then boom, a new discovery changes everything.
This deep dive has been a whirlwind. We've gone from the power of fluorine to the mysteries of heavy elements and even the strange world of extreme temperatures.
And we've seen how these fundamental forces shape everything around us, from the materials we use to the technology that powers our world.
I feel like I've learned so much about chemistry and its power.
That's fantastic to hear. As scientists, that's what we love, to spark that curiosity and sense of wonder. And remember, this is just the beginning. There's so much more to discover.
Absolutely. Well, to all our listeners out there, keep exploring, keep asking questions, and never stop learning. Thanks for joining us on this deep dive into black holes in chemistry. We'll see you next time when we'll uncover even more secrets of the chemical world.